Okay, nice to see you all. Sunny day, it's all good. Right, so we'll see how far we get today. So I'll tell you a bit more about having set up this G-structure language, how we can use it for supersymmetric backgrounds. And then I'll try and start talking about backgrounds with flux, and we'll just see where we get to. And maybe we can make some choices along the way. You can tell me if you'd rather see one thing rather than something else. Okay, so let me just remind you where we were. So we had two ideas. So we have given a frame bundle, f of m, and some group G inside GLDR. Let me do this oscillation. A G structure was a principal G subbundle, P inside the frame bundle. So that was a set of frames that transformed under a subgroup G. And then we said that a torsion-free G structure or sometimes integrable, that correspond to one, that was one where there exists a connection that is compatible.
Should we shift the stand, because it's just standing on one leg there.
Oh.
This is just, I don't know what will happen if I'm...
Thank you. It's compatible with the G structure. That means if the G structure is defined by some invariant tensors, when you take its derivative, it vanishes, and has vanishing torsion. Right, so a special G structure, this is a special class of G structures where you can find a connection that's compatible with the G structure and its torsion vanishes. And there was this thing called the intrinsic torsion, which is the obstruction to finding a torsion-free structure. So the intrinsic torsion had to vanish in order to find one of these connections. Okay, questions about that? We're good? And then over here, I had this table of supersymmetric backgrounds. So the idea was we were going to just look at Minkowski space type backgrounds. So we're going to look at spaces where our manifold with some Minkowski space, so this was the simplest type of supersymmetric background we could think of, times some internal space. And we needed, remember the variation of the bosons was equal to fermions. And this was automatically 0 because our background was purely bosonic. And then the variation of the fermions, all basically you had to have some covariantly constant spinner with respect to the Levi-Civita connection. That was if we take no flux. So these are backgrounds that are purely metric. You write down the variation of the spinner of the fermions. They depend on a parameter, which is the supersymmetry parameter, and they depend on derivatives of that. And in general, if the variation of the fermions is going to be 0, that tells you that this derivative has to vanish. But then we have this nice picture that we can think of the pair G and eta as defining a G structure where P, where the group G lives inside OD, has to live inside OD because a metric will define OD, and the group G will be the thing that leaves the spinner invariant. Okay? And the fact that this is 0, since we're looking at a G structure that's a subgroup of the orthogonal group, we know that for the orthogonal group there's a unique torsion-free compatible connection, that's Levi-Civita. So this connection that's going to be torsion-free has to be Levi-Civita, and the fact that the spinor is 0 is telling you that it's compatible with the G structure. So this condition is the same as the condition that this is a torsion-free. Okay? So now we just go through a procedure where we look and see, so this is what I wrote here, I guess. We need to go through and find all the different groups that preserve the spinor. So really, right, it's a subgroup of spin because it lives in spin, and we need to act on the spinor and come back to the spinor. And then you just go through and you see what the groups are. And these are the basic cases. So if we're in 4 dimensions and you have a single solution to the killing spinor equation, so you just have one spinor satisfying this, that gives you, if you like, one supersymmetry. And the group then is SU2. If you go to 6 dimensions and you have one, it's SU3. If you go to 7, it's G2. And if you go to 8, you can have 1, 2, or 3 spinors. And if it's 1, it's some spin 7 inside spin 8. If it's 2, it's SU4. And if it's 3, it's the symplectic group SP2, which is the group of quaternions, right? I don't know if you're thinking about that, or you can also think of it as a group which is both unitary and symplectic. And these different cases correspond to known geometries. So these ones that are all SU, SU2, SU3, SU4, those are Calabi-Yau manifolds of 2 complex dimensions, 3 complex dimensions, and 4 complex dimensions. G2 is called a Joyce manifold. Spin 7 is usually just called spin 7. Sometimes it's called a Cayley manifold. And this SP, these are hyperkähler manifolds. Okay, so I'm going to tell you now a little bit about each of those. But do you get the basic idea? The idea is once we've set up this language, solutions to the having a supersymmetric background is just one-to-one the same as a G structure. And what G is it? It's the group that preserves the spinor. The subgroup of spin that preserves the spinor. Ask me questions.
And it doesn't matter if you are compactifying from M theory or...
Right, so this could be, in this case, because we turned off all the fluxes, it doesn't really distinguish type 2 and M theory. The difference will be exactly the spinor groups and so on. So I'm just sort of putting that under the rug. But in the end, you'll end up with a spinor on some d-dimensional manifold. Yeah?
Could you maybe, so the group is the little group of the spinor, so to speak.
Yeah.
And so can you just maybe explain again how you're getting or at least how the manifold is determined from that?
Why don't I do an example and then maybe is that a good way to do it? Yeah, okay. All right, so let me just say let me just finish the table and then I'll come back to that question. So okay, you could also, in any dimension, so you could also, so now we have dimension D, so that's just D. We have the number of killing spinors. This is just going to be the dimension of the spin representation, spin D. And then the group here, I'm just going to take the trivial group, right? So that's the strongest structure I can have, right? Remember, that's the same as saying, so if we have what's called an identity structure. What's an identity structure? It's the same as just picking out a single frame, a single global frame, right? Because remember, any 2 frames are related by a transformation of the group. If the group is trivial, it's just got one element, the identity, you just get a single frame. And this is just flat space. Right? Or more generally, or it could be a d-dimensional torus. Right? So that's the sort of extreme case. And just to say I can put these together, you can put things together. So these are sort of the building blocks. So for example, I could take d equals 8 and take M to look like the product of two four-dimensional manifolds and take the group to be SU2 times SU2. So that's like two copies of this one. Or I could take, say, d equals 7 and take it to be a circle times a six-dimensional manifold and have a group which was just the identity times SU3, which is just SU3. Right? So I can build things in other dimensions out of these building blocks. I can always add in some torus, and I'll get more, right? So. Okay. So let's do an example. So I'm roughly going to go through these cases. So let's do an example. So why don't we do SU3? So just to remind you, so we start with a little bit of group theory. So you need to remember that spin 4, so we have some G inside O6 inside GL6, that's what we're expecting, right? And spin 6, if you remember, is isomorphic to SU4. It's the same group as SU4, the connected, simply connected Lie group. And the spinners transforms in the 4 of SU4. Right? It's a 4-component spinner on a 6-dimensional manifold. You write down some gamma matrices, that's how it works. So if we take for a fixed spinner, so we're taking some solution, let's just imagine that it just had the first component non-zero. We see that it's stabilized by SU3, right? I want to take the S transformations of SU4 that leave one of the components of the spinner invariant. That's just SU3. And so that tells us that that tells us that the group we're interested in so it tells us that if we have the pair, which is metric and spinner, are stabilized by SU3. Right? The metric stabilized by O6, and then if we in addition have the spinner, that puts us into an SU3 subgroup. And although this SU3 was a subgroup of spin 6, it's actually also a subgroup of SO6. So you don't have to worry about the fact that it came from the double cover, right? So what's the structure? What are the structures that we have? So the invariant tensors so remember, in general, the G structure can be defined by a set of invariant tensors. I hope I'm sort of answering your question. So in this case, there's two of them. So the invariant tensors are a pair of objects. So this thing is a 2-form. and this thing is a complex 3 form. And you can construct them from this data. So explicitly, let's given gamma matrices. So let's suppose we got some set of gamma matrices. Right? Those are the gamma matrices for spin 6. And a frame and an orthonormal frame for G, right? So we take one of the orthonormal frames for G. We can build this thing, we can build omega in the following way. It's actually just I eta bar gamma AB eta E this AB EA wedge EB. So these are the elements of the dual frame. And you can construct the 3 form as eta transpose gamma ABC eta EA wedge EB wedge EC. Probably I want a 1 on 2 factorial there and a 1 on 3 factorial there. Okay, and these gammas here, when I write gamma A1 through AN, I just mean the anti-symmetrized product of that number of gamma matrices. So I get some set of gamma matrices. They're automatically anti-symmetric on these, so I'm going to get a 2 form and a 3 form. So concretely, if I have the metric and the killing spinner, I can construct these 2 invariant things. And since they're built out of the metric and the spinner, they're going to be invariant, right? I'm building them out in invariant objects. Equivalently, actually, if I specified these 2, you could go back and define these 2. Okay? And then you also get, these are not general 2 forms and 3 forms, but they satisfy the following conditions. So if you take the wedge product between the pair of them, you get 0. And if you take 1 on 3 factorial times omega wedge, you get 1/8 I of omega bar, capital omega wedge, capital omega bar. So when you construct them this way, they necessarily satisfy these conditions. Put another way, if you just chose some 2 form and complex 3 form that didn't satisfy these conditions, they wouldn't be stabilized by SU3. They're only stabilized by SU3 when they satisfy these compatibility conditions. Okay? Does that make sense? Okay. And then you can work out what the torsion-free condition means. And you find that it just says that d omega is 0. And altogether, this is the conditions of a Calabi-Yau threefold. So if you can find a 6-dimensional manifold with a pair of forms on it that satisfies these conditions, then you know, then it's a Calabi-Yau. Questions? Yeah.
So we found in this case that the stabilizer group of the killing spinner sat nicely inside 06.
Yes.
One is, it doesn't seem like that would always be the case for any space.
Fortunately, it is. Yeah.
Oh, it is.
Yeah. 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 Any other questions? You can have, yeah. Okay, I slightly lied. So there's an issue in the literature as to exactly how you define these manifolds. So for example, for Calabi-Yau, it will always work. For G2, there's actually two slightly different definitions of G2, whether it has the killing spinner or doesn't have the killing spinner, exactly. And it's to do, is that the best example? Let me think. Maybe that's not the best example. No, when we talk about Sasaki-Einstein manifolds, that's true, and it's to do, but up to some discrete group, which almost always you don't have to worry about, it's not going to be an issue. Yeah. Sorry, that wasn't a very helpful answer. Okay. So let's just say a little bit more about these things. So these are actually complex spaces. These are complex manifolds.
Sorry,
Yeah, let me just write this. Yep.
Calabi-Yau, is it defined by these two properties, or we can kind of come up with?
There's multiple ways of defining Calabi-Yaus. So I'm defining it this way, sort of through G structures, which is not the way it's usually defined. So it's usually defined as a Kähler manifold with a vanishing first-gen class. So I'm going to say a little bit more about that now to connect it more to what the way you might normally have seen it. So first of all, I'm claiming these are complex manifolds. So how does that work? So if you remember, if we had a complex structure, that was an I, right? That's squared to -1. And it allowed us to decompose the complexified tangent space into two eigenspaces. Right? This was this general G structure. So this was, right? This is going to be a GL3C inside GL6R structure. And remember, for G structures, you can decompose tensors into representations of the group, and that's what we're doing here. So this has got the plus eigenvalue and minus eigenvalue under the action of I. So to know that this is a complex manifold, I need to understand what these, but how do I get those bundles? Well, you can think of them they're defined using omega. So here, these holomorphic vectors, or the anti-holomorphic vectors, are going to be the ones that are in the complexified tangent space, such that when I contract them into omega, I get 0. Okay, so this notation, this interior, are people happy with that? That just means Vm omega m n p. I just contract the vector into the first index. So this defines a subspace, and so this actually tells you, so this implies that actually this omega you can think of as a section of the nth power of the holomorphic bits. So it's an n form, right? And we're on a 2n dimensional map. Sorry, this is a 3 form. So it's a 3 form. We're on a 6-dimensional manifold. When we split this thing, we could take 3 forms that are just built out of, sorry, I want the dual. I could take the dual of this space, so that's like the 1 form bits, and then I can take 3 forms just built out of the dual. And in fact, that's where this omega lives. Okay? So if you think of it in terms of holomorphic and anti-holomorphic indices, it's just got 3 holomorphic indices. Okay, so this defines this subbundle, but it better be integrable. So remember, to be an integrable complex structure, what do we need? We need that if you take the Lie bracket between two things in the, so for all VW that are anti-holomorphic things, if you take their Lie bracket, that also had to be anti-holomorphic. Remember that involutivity condition? So let's see if that's true. So let's check. So let's take the Lie derivative. So we know we know that 0 is the Lie derivative of IW into omega, because this is 0, right? So let me just take the Lie derivative now along another vector v. But this is just equal to I times the Lie bracket of these things, right? This acts on here first, contracted into omega, and then I'll get IW, and then I'll get the Lie derivative of omega. But if you remember the formula for the Lie derivative, this is just d IV omega plus IV d omega. But this is 0, and this is 0 because it's an anti-holomorphic vector. So we see that this is just this. So when I contract with the Lie bracket, it's also 0. So that just tells me that the Lie bracket indeed is a section of T01. So from this structure, we can define an integrable complex structure. And that actually means that we can introduce complex coordinates. So I told you that if you have an integrable complex structure, that means you can have complex coordinates. And if I just take the pair, which is just these two things, that tells me it's a Kähler manifold. So Calabi-Yau manifolds are a special type of Kähler manifold. And the special condition is that they're Ricci flat. So I'm going to come back to that. Okay? And, okay. So there's a whole load of stuff which we're just, which is super useful, which I'm not telling you anything about, which is once you've got a Kähler manifold, it's complex. So you can use complex coordinates, so you can use algebraic geometry. So there's tons of tools in algebraic geometry that you can use to tell you about Calabi-Yau manifolds. And they're special because they're complex and because you've got all those tools. So for example, there's an incredibly important theorem, which is the Calabi-Yau theorem, which is about the existence of Calabi-Yau structures. So we needed to find a pair, omega and big omega, that satisfies those differential conditions. So if I give you a manifold, you go away and you write down those differential conditions, and you have to solve some nonlinear partial differential equations. That's hard, and in general, you can't find solutions of them. However, there's a Calabi-Yau theorem that says if you have a complex manifold with certain properties, you can guarantee that there's a solution. And you can also work out quite a lot about the solution without knowing it. So that's why we can do a lot of stuff with Calabi-Yau manifolds that we can't do, for example, with G2 manifolds, where no such theorem exists. Okay? So there's a whole lot of stuff I could tell you about that, but I guess I'm not going to. Okay, so this extent, right, so we did the case of Calabi-Yau threefolds. So for Calabi-Yau n-fold, you would have some omega, which is a 2 form, and some capital omega, which is an n form. So this is an SUN inside GL2NR. And again, you would have these same conditions, and you'd have some 1 on n factorial omega wedge n times was given by, and then there's just some combinatorics, which if I remember is n, what did I write down? m plus 2 over 2 factorial. So again, there's some normalization conditions. And what's going on here, so you can think of this as we have a GL 2nr structure. And then inside there's a symplectic structure that's defined by omega, with d omega equals to 0. And then there's also inside here actually an SL-NC structure, which is defined by omega, capital omega with d omega is 0. So if you remember, the complex structure was a GL3C structure. The difference between having the complex structure I and having the form omega is just that it fixes the determinant. So it's now an SL-NC structure rather than a GL-NC structure. And then you can have a common subgroup, which is SUN, which is defined by the pair. Okay? And only if they satisfy these conditions is the common subgroup SUN. If you didn't satisfy those, it would be some other smaller group. Okay, so let's just say something about this Ricci flatness. So Ricci flat. So all the supersymmetric backgrounds are Ricci flat. That means their Ricci tensor vanishes. So you can do a simple calculation to show that. So let's remind ourselves. So recall we had that the Levi-Civita derivative of the spinor was 0. So let's do the following thing. Let's contract with a gamma matrix and take the action, the commutator of two Levi-Civita derivatives acting on the spinor. Now, if you remember your GR, if you take the commutator of two derivatives, you get the curvature, right? So this thing I can write as gamma m, and then here I'll actually get, the way it works is I'll get a quarter r m n p q, and then I get a pair of gamma matrices acting on this spinor. And then I do some gamma matrix algebra, and I can either take the symmetrized products here or the anti-symmetrized products, and the effect of that is I get two terms. So I get R, M, N, P, Q, gamma N, P, Q acting on the spinor. And then I get another term which looks like 2 R, M, N, gamma N acting on the spinor. So I just did some gamma matrix stuff. So I'm basically using here the fact that gamma m, gamma n is 2 GMN. But this first term, right, this is anti-symmetrized on these indices. That's 0 for the Riemann tensor. So I just get this. So that has to be 0. And then I have to do a little trick, which is that tells me that this tells me, in fact, that then if I take a pair of these things, R, M, P, gamma P, R, M, Q, gamma Q acting on the spinor, this will also be 0 because the second factor acting on it is 0. I do some more gamma matrix tricks, and this just becomes R, Mn, R, Mn, acting on the spinor as 0. So the square of the Ricci tensor has to vanish. The metric's positive definite, so that tells me that the Ricci tensor itself has to vanish. Okay? This is the sum of squares this is the sum of squares, so each thing has to vanish separately. Note that this step requires a Riemannian metric. So that this is a sum of squares. If it was a Minkowski signature metric, I'd get some minus signs there and it wouldn't have to vanish. So this argument only works for Riemannian spaces. If I try to do the same thing on a Minkowski type space, it won't necessarily vanish. Okay. So that's the special condition on this Kähler manifold. The extra condition that comes, the final condition of supersymmetry is that it has to be Ricci flat. Okay. All right, so let me tell you about some of the other ones. So there were also these groups, there was these hyperkähler manifolds. So they're ones where you have a group SPN, which is inside GL4NR. So this group SPN, you can think of it as a group of quaternionic valued matrices that preserves an inner product. I don't know if that's something you're used to. If you're not used to that, this is the same. This is sometimes called USP2N, and that's the group of matrices in SU2N, such that they also preserve some symplectic form, where omega is something like -1, 1, -1, 1. Okay? So they're both unitary and symplectic. It's just the right. This is just in the classification of semi-simple Lie groups, right? This is just the one with a double root, with a short root with a double line. So what are the structures here? Well, you actually get a triplet of symplectic forms. So you get 3 symplectic forms. So it turns out the thing that's invariant under the things that are invariant under this group is these 3 two forms. Now again, they have a condition between them, so they all satisfy that. So I think what the best way to do this is. They satisfy omega 1 wedge omega 2 omega 1 is equal to omega 2 wedge omega 2 is equal to omega 3 wedge omega 3. And omega 1 wedge omega 2 is equal to omega 2 wedge omega 3 is equal to omega 3 wedge omega 1 is equal to 0. And then in addition, they're all closed. So then the torsion-free condition just tells you that they all are closed. And again, I could write them in terms of the killing spinors as bilinears, but I'm not going to do it. You can actually do the following. You can define a set of inverse objects which live in wedge 2 of T. So they're things that are bivectors, they're things upstairs. And if you contract them, you get delta ij times the identity. So what I mean here is I'm going to take MP Wj inverse Wj np. So by definition, that's why I put an inverse here, because they're the inverse of this guy. But then you get an extra term when they have different indices. And this gives you a triplet of complex structures. So from the omegas, you can actually construct 3 complex structures. So this setup is like, it's both, it looks like it's just 3 copies of a symplectic thing, but actually for each one there's a corresponding complex structure, so it's more like 3 copies of a Kähler thing. And what it's trying to do is to these are like the three ijk that appear in quaternions. So these are like ijk for quaternions. So I don't know if you've seen quaternions, so let me just assume you have. So there you define some generalization of a complex number that depends on 3 things. And again, each of these squares to -1. Right? Have people seen this before? Yep. So what this is trying to do, so the geometry almost has quaternionic coordinates. So with the complex structure, we were able to introduce complex coordinates. This geometry is sort of wanting to introduce quaternionic coordinates, but it doesn't work. You can't actually introduce local quaternionic coordinates. Even though you have these 3 integrable complex structures, you can introduce complex coordinates for each one of them, or some combination thereof, but you can't do it simultaneously in a way simultaneously, so you actually get quaternionic coordinates.
So that's not almost in the structure language?
No, this is almost in just like some poorly defined language. Good. And just notice that if I take the special case of SP1, this is just the same as SU2. So hyperkähler is the same as Calabi-Yau in this case. How does that work? Well, this is just, we have omega is omega 1, and for SU2 Calabi-Yaus, we have capital omega will be a 2 form. So we can just think of that as omega 2 plus I omega 3. And this space is the famous K3 manifold. So the Calabi-Yau in 2 dimensions is also hyperkähler. And in fact, there's only one example, one compact example. There's only one such manifold, if it's compact, and that's this K3 manifold. If it's non-compact, you can do more things. Okay? And then, what about the other ones? Well, G2, we sort of already talked about. So I think just to complete the list, I need to tell you about spin 7. So that's a spin 7 that lives in GLAR. And the invariant tensor, So here we had an invariant tensor that was phi, a 3 form, and we needed d phi is d star phi is 0. Now we get an invariant tensor which is a 4 form. So let me write it using a frame. So, do I want to write this out? I will, I'll give it to you. So it's got 1, 2, 3, 4, 5, 6. It's got 14 terms. But it's got a pattern to them. So 1, 2, 3, 4, 3, 4, 5, 6, 5, 6, 7, 8. Oh no, I'm not getting it. Okay. Sorry. 1, 2, 3, 4, 1, 2, 5, 6, 1, 2, 7, 8. So I'm thinking of them as pairs. 1, 2, 3, 4, 5, 6, 7, 8. So I do 1, 2 with each of the other pairs. So 1, 2, 3, 4, 1, 2, 5, 6, 1, 2, 7, 8. Then I add to that E. Now I do the 3, 4, 5, 6. Then I need to add E 3, 4, 7, 8. And then I have one more, which is E 5, 6, 7, 8. So I've done all the pairs of pairs. And then, oh, I haven't got enough space. Let me write plus delta. I'll now go over here and I'll tell you what delta is. So what I'm writing here is when I write E1, 2, 3, 4, I mean E1, wedge, E2, wedge, E3, wedge, E4. Right? So you need to have the frames. And then the extra bit delta is, so now I take all the odd ones, E1, 3, 5, 7. And then I can change any two of them to an even, and when I do, I get a minus sign. So I get E2, 4, 5, 7. I changed 1 and 3. E2, 3, 6, 7. I changed 1 and 5. Oh my goodness. 2, 3, 5, 8. I did 1 and 7. Now I can do E1, 4, 6, 7. I do 3 and 5. E1, 4, 5, 8. How am I doing? 1, 2, 3. 4, 5, 8. And then I can do E1, 3, 6, 8, and then I could change all of them, and then I get an overall plus sign, 2, 4, 6, 8. Okay? So it turns out that the subgroup of GL7 that leaves this thing invariant is exactly a spin 7 group. And it's a weird spin 7 group because the vector of the vector 8 of SO8 remains an 8 of spin 7. So you might have thought I would have gone from SO8 to SO7, the vector I'd pick out one direction, it would decompose into a 7 plus a 1. That's not what happens here. And what we're using is we're using triality of SU8. So if you know about SU8, it's got that Dinkin diagram. It's got 3 8-dimensional representations. There's a vector 1 and there's 2 spinor 1s. And what's happening here is the spinor 1 is decomposing into a 7 plus a 1. And the vector 1s are staying as 8-dimensional representations under spin 7. Okay? That's just saying I get one spinor, right, which is the killing spinor that I'm picking out. Okay, and torsion free just tells you that D of this object is 0. It's very simple. Okay. Questions? Okay, so I see that it's getting to 25 past. I think we have some choices now. So I want to start telling you a little bit about what happens when you turn on the fluxes. One thing I haven't done is told you the relationship between this and special holonomy. So all these spaces also are actually special holonomy spaces. And that's straightforward to see when you have a G structure. So when you have a chosen-free G structure, it will automatically have special holonomy. So I could give you that little proof, but I think I'm not going to. I think I'm just going to tell you that you believe that. Okay? So instead, I'm going to start telling you about fluxes and what changes when you turn on the flux. And I'll focus just on the ones that are relevant for ADS CFT. And then at the end, I'll just I'll wave my hands and tell you how you can do it completely in general. Okay? Does that sound like a good plan? And I'm thinking then, should we try and stop at 12:15? And then I'm just going to keep going. You're not going to get a break. Is that all right? Okay. All right. Okay. So let's try that. So so NB, all these manifolds have special holonomy. Where the holonomy group of the Levi-Civita connection is contained inside the G structure. So generically, it will actually the holonomy group will just be the G structure itself. So for a Calabi-Yau threefold, the holonomy would be SU3. For a G2 manifold, the holonomy would be G2. And that just follows directly from the definitions of a G structure. Okay. All right, so let's okay. So let's think about some simple some simple SUSY backgrounds with flux. So you can see the issue, right? Before we just looked at covariantly constant spinors because all the flux vanished. Now we're going to have contributions from the flux. So what happens? That's the question. So let's consider ADS backgrounds. So we'll look at something now where we have some ADS space times some internal manifold. And we're going to have a metric which is going to be just the metric on the ADS space plus the metric on the manifold internal space. And we're going to have one flux. So I'm going to have some F, which is N1 through ND. So it's a top form on M. So I'm going to allow just one bit of flux, and I'm going to require that it's just a top form on here. Okay? Fluxes are described by forms. So what examples? So the two key examples here are going to be, so we could do in M theory, we could have ADS 4 times some internal space, and our flux will be some seven form flux, which is like the Hodge dual of the 4 form flux. So you remember in 11-dimensional supergravity, there's a 4 form flux. I can have the 4 form flux on ADS 4. If I take its Hodge dual, it looks like a 7 form flux on M. So let me think of it that way. Is that all right? And this corresponds to the backgrounds that look like M2 branes. Right? These are like the duals of M2 branes. And then the other classic example would be in 2B. I could take ADS 5 times some 5-dimensional space. So this is some 7-dimensional space. This would be some 5-dimensional space. And here we just take the Ramon-Ramon flux, the 5-form Ramon-Ramon flux. And these are like D3 branes. Okay? So the question we want to ask is, what are the conditions on these guys for this to be supersymmetric? To preserve some killing spinors. Is that the setup okay? Okay. So what's going to change? So what do we need to solve? So as usual, we need to solve. So again, the variation of the bosons is 0. We've already got that. For the fermions, well, what do we get? So we're going to have something like I wrote this down before, so we have something like some Levi-Civita derivative of our spinor, and then we'll get some contribution from the flux. So let me just write it like that. And there may be, that's if it's gravitinos. If there's also some dilatini, I might also have something like this, again with some flux term. So it's no longer going to be just that this is 0, right? Now what's the idea? So the idea is, first of all, you can still define a G structure from the pair G eta. Okay? So there's still going to be some solution to the killing spinor equations, which will give you some eta. So you can still think of a G structure, but it's no longer torsion free. Because the Levi-Civita on the spinor is no longer 0. So in other words, so the mantra is going to be is that flux corresponds to intrinsic torsion. Right? Because remember, the intrinsic torsion was what measured the lack of integrability. The flux is forcing us to not be integrable, to not be torsion free. And so we can think of the flux as being related to the intrinsic torsion. So we'd expect to get backgrounds which are no longer torsion free but have some kind of intrinsic torsion. Okay? So for these examples, we find that SUSY background corresponds to G structure with singlet, with constant singlet intrinsic torsion. So I'm going to explain what that means. So what you can do is you just go through, you take these equations, you construct the invariant tensors, you turn some handles, you work out what the intrinsic torsion is, and what you find that it's always a singlet, constant singlet. Okay? So let me explain that, and I think the easiest one to do is actually the G2 case. So let's do an example. Let's do ADS4 times M7 with a single killing spinor. Right, so just one supersymmetry. So again, for the structure, we have the pair G eta. But remember, I told you on M, but I told you from the last table I wrote down, if we have these two, that defines a G2 structure, right? Because I'm in 7 dimensions with a single spinor, that defines a G2 structure. So we have Okay, so let's do a little bit of representations. So we have G2 inside GL7R. So let me do some decompositions. So if I have the tangent bundle or the cotangent bundle, they live in the 7 representation of, so this is GL7, this is G2, and the 7 just stays as the 7. If I have two forms in 7, that's the 21-dimensional representation, that decomposes under G2 into a 7 plus a 14. So I'm just doing some, you can go look these up in Slansky or something. And then if I take 3 forms, they're the 35-dimensional representation, and they decompose into a 1 plus a 7 plus a 27. Okay? And you knew this 1 had to be there because this is just the invariant 3-form phi of the G2. There's a 3-form invariant 3-form. Okay. So let's do the intrinsic torsion calculation. So remember we have the space of connections, right? If we shifted 2 connections, that was something we called omega, which had MNP, and this had to be a section of T star M tends to the adjoint of G2, right? That was the whole point. Different compatible connections had to act in G2 in the group. So if you think about the representation theory, this is going to be something which is in the 7 times, well, the adjoint of this one, this is the adjoint of G2. If you remember the adjoint of the orthogonal group, right, that's anti-symmetric things, so that's the 21, that's the adjoint of SO7. So this is the G2 lives in SO7, that's the 14. So the space of connections lives in that representation, the 7 times the 14. The torsion, right, that's something which is TMNP, TMNP. That's something which lives in, it's got a vector and a 2 form. So that's going to live in, well, a 7 for the vector, and then for the 2 form, it's going to be 7 plus 14. So this is the space of torsions. This is how much we can shift around in that space by changing our compatible connection. So you see that the 7 times the 14 here we can eliminate by choosing our connection, but we can't remove the 7 times the 7. Okay? Does that make sense? So we see that the intrinsic torsion we call it T int, is going to live in something which is the 7 times the 7. And if I look at the tables for G2 and work out the tensor products, that's given by 1 plus 7 plus 14 plus 27. So you notice that there's a singlet there. Okay. Now, just to see how that matches up, if we think about d phi, that lives something in wedge 4 T star M. Now, in terms of representations, wedge 4 is like wedge 3, right? Because they're Hodge dual to each other. So that's going to have a 1 plus a 7 plus a 21 in it. And d star phi, that lives in wedge 5 t star m. That's like two forms, 5 and 2 are dual to each other. So for two forms, that's the 7 plus the 14. So you can see explicitly that the 1, 7, and 27 components of the intrinsic torsion appear in d phi, and the other bits appear in d star phi. Because I told you if d phi and d star phi vanished, then the intrinsic torsion vanished, right? So all these representations have to appear in these exterior derivatives. So all I'm doing is decomposing things into G2 representations. That's all I'm doing. But here's the interesting thing. We've got this singlet, so we can have singlet torsion. So what's it going to look like? We're going to have d phi. Well, it's got to be some 4 form which is invariant. The only invariant 4 form is star phi. So it has to be some multiple of star phi. And then d star phi is 0, which actually follows from the line above. So lambda is the singlet torsion. Okay? It had to be something that was invariant under the G2 group. It has to be a 4 form. The only thing you have is star phi. And in the solution, in the SUSY background, lambda is constant and proportional to the ADS radius. Right? There's one length scale in the problem, which is the size of the ADS. Sorry, ADS radius to the inverse, I guess. ADS mass. Right? There's one length scale, one mass scale, so that's basically what has to appear here with some suitable number. So this is what's called a weak G2 manifold. It's almost integrable, but not quite. Any questions? You okay? Okay. So what if we had, that was one supersymmetry. What if we had two supersymmetries? So now we've got sort of G, and we've got eta 1 and eta 2. We've got two spinners. And it turns out the group now, so now the stabilizer group is like, is actually SU3. But SU3 in 7 dimensions, not SU3 in 6 dimensions. So what are the invariant tensors? So the invariant tensors, I'm going to have 3 things. I'm going to have the ones that you have on a Calabi-Yau, and then I'm going to have one extra direction. So this thing's going to be a 1 form. And if you like, this is sort of the 6D part, and this is the 7th direction. So some E hat 7, right? Some E7. So to define the structure, I first need to go from 7 to 6. That's what this little sigma direction depicts out. It just picks out the 7th direction. And then on the 6th part of the space, I need something that looks like Calabi-Yau. So I've got omega, the 2 omegas. Okay? Now you can again, so this is an example. You remember I told you could have structures on products. So where it was something like, 6 and you put a torus on the rest. So if this was torsion-free, everything here would have to be closed. But again, you can have singlet torsion. And what you find is that d sigma is equal to 2 lambda omega, and d big omega is, is 4I lambda sigma wedge big omega. So again, the exterior derivative of sigma, that's a 2 form. I have an invariant 2 form, which is this omega, so I can put it there. And similarly, the exterior derivative of big omega has to be a 4 form, and there is one which is sigma wedge big omega. There are other ones as well, but this is the one that appears. Okay? And note from this, it follows that d omega is 0. And these are the conditions of what's called a Sasaki-Einstein manifold. But again, it has constant singlet torsion. Let me just make some more comments. So note you can define a vector xi, which is usually called the Reed vector. And I can define it by saying its contraction with sigma is 1, and its contraction with the omegas vanishes. So it's sort of like, this is like E7 hat, right? This is like the vector in the 7th direction rather than the 1 form in the 7th direction. And you can show, so just from these conditions, from the conditions, you see that the Lie derivative of omega is 0, and the Lie derivative of capital omega is 4I capital omega. And from these, this actually tells you that the Lie derivative of the metric is 0. So this is a killing vector. And what it does is it generates the U1R symmetry of the dual field theory. So with this number of supersymmetries, there should be a U1R symmetry in the field theory. So you ask, what's the dual of that? That will be some killing vector field in the geometry, and it's just defined by the structure. Okay? So let's do one more just for completeness. So if we had 3 supersymmetries, you then find that the structure is given by, so now you have a SU2 structure, which is the same as SP1. And the invariant things are a triplet of 2 forms and a triplet of 1 forms. So this is like a 4D, 3D split. So it's like we're splitting again. If it was integrable, this would just be a 3 torus, and this would be K3. But it's not going to be integrable, so it's going to have that structure, but it's going to have different conditions. And you find that you get the condition that d sigma I is given by 2 lambda omega I minus lambda epsilon ijk sigma j wedge sigma k. And from that you can work out what d omegas are. And this is what's called a tri-Sasaki manifold. And it's sort of like exactly just as like this was a bit like Calabi-Yau, this one's a bit like hyperkähler, and instead of having, you now get SU2R symmetry. So you can define a set of vector fields that are orthogonal and that are the analogs of these guys, and then they leave the metric invariant and they satisfy the SU2 algebra. And in general, in each case, you can consider the cone geometry. So let's think of a space X, which is topologically some positive real numbers times the manifold, and we can take some metric on this bigger space, which just looks like the cone geometry on that space. So I have a coordinate r. And if M is weak G2, then X is spin 7. If it's Sasaki-Einstein, then X is Calabi-Yau. And if it's Tri-Sasaki, then this space is hyperkähler. So another way of thinking of these spaces is that such that the cone over them is one of the integrable cases, spin 7, Calabi-Yau, hyperkähler. Okay? And that's characteristic of all these ones with singlet intrinsic torsion. Okay, so again, there's more we could say there. But in the last, little bit, let me try and give you an idea about what you do if you've got more fluxes. First, are there questions on this? Yeah.
It's not clear to me how we used precisely the flux. It seems that we used the fact that the spinner wasn't parallel with respect to geometry, but I don't really see how we used the fact that our flux was a top form of space. Good. So I totally glossed over all of that. So I should have said something a little bit more. So if you remember, we said this was a top form. So it's a singlet of SOD, right? The top form transforms trivially under SOD. So that means it's also going to be a singlet of G, because this is always a subgroup of SOD. So whatever flux, the way I constructed it was that I turned on a flux that was necessarily a singlet. So that means whatever I should have said that. Whatever the intrinsic torsion was, since it's coming from the flux, it better be a singlet. That makes sense? Yeah. And also from its equation of motion, you know that this is true. And that tells you it's a constant with respect to Levi-Civita. So that's why it's a constant intrinsic torsion. Other questions? Okay. So what about in general? So what about general flux backgrounds? So we expect somehow that somehow the flux should correspond to intrinsic torsion. However, if you start working it out, you find a couple of difficult things. So the first thing is that this is just complicated. And these are not singlets, for example. And you just sort of get structures that have less and less integrability. So you sort of have less and less structure as you turn on more and more fluxes.
The second point, which in a way is more problematic, is that in general, the G eta pair doesn't define a global structure. So what do I mean? In particular, in general, if you take the Levi-Civita derivative of this magnitude of the spinor squared, this is no longer 0. Sorry, if you, I shouldn't say that, sorry. I should say, yeah, if I just take the, that's all right. If I take the Levi-Civita derivative of the magnitude of the spinor squared, this is no longer 0. If when you move around the manifold, the spinor is just transforming in spin, the magnitude of the spinor squared should not change, should be a constant. But what happens with the presence of the flux is the magnitude can change. And what that means is that at one point you can have a spinor that's stabilized by SU3, at another point it can be stabilized by G2. So you don't know what to do. You don't know whether to think of it as a G2 structure or think of it as an SU3 structure that at some places becomes G2. So that's a real problem. Before we go further, I should tell you something else. So for compact manifolds, there's a key no-go theorem. Ooh. So there are no SUSY backgrounds with non-trivial flux, unless you have sources. Okay? So you need to have some sources for the flux. So you need some branes in there or some orientifold planes in general. Okay? But that's not true for, that's for flat space. It's not true for not ADS. I've given you examples with fluxes and ADS. Okay. All right, so how do you try and get around this problem? So what you would really like to do is still have some kind of integrable structure. So I should say one of the most important things you might want to do for a given background. Let me chat for a moment. I've told you what all these structures are that correspond to different supersymmetric backgrounds, right? Great. That's not really the problem you're interested in. You're interested in finding examples, right? I've given you a nice way of describing them, but the question is, can you actually construct them? And once you construct them, can you work out their properties? And one of the key properties you might want to do is moduli. If I have a Calabi-Yau background, can I distort it so that it stays Calabi-Yau? Can I distort a G2 so it stays G2? If I can, in the low energy theory, that's a massless degree of freedom. That's a key problem in doing phenomenology, right? You want to compactify on some background with a certain amount of supersymmetries to match the standard model. You get some massless scalar fields if it's got moduli. You're also interested in that question for ADS CFT because moduli there correspond to marginal deformations of the field theory. You can deform the background, it stays ADS. That's a marginal deformation. If the radius of the ADS doesn't change, the central charge isn't changing, and so that's a marginal deformation. So the two things you'd really like to do is to be able to construct solutions and find moduli. Okay. For Calabi-Yaus, there's the Calabi-Yau theorem. That's great. Because you just have to do some complex geometry, and then the Calabi-Yau theorem tells you there will be solutions. And furthermore, you can calculate the dimension of the moduli spaces just knowing the complex geometry. For G2, it's much, much harder. So there are now more ways of constructing G2 manifolds, but they're very detailed. You have to glue things together in particular ways. We're missing at the analog of the Calabi-Yau theorem. Okay? For these fluxy backgrounds, even harder, right? You'd love things which are analogs of the Calabi-Yau theorem. So that's one direction the research is going, is trying to understand how to write down things which are analogues of the Calabi-Yau theorem for those backgrounds. But despite that, you might still be interested in calculating moduli. That's a key problem. So someone might give you quite a complicated background, and you want to find all the moduli. Now, if you have one of these backgrounds and you describe it in terms of some intrinsic torsion that's like non-integrable, the moduli problem becomes very difficult, because you're trying to sort of vary things with a source, which is the intrinsic torsion, and what do you do with the intrinsic torsion? Do you vary it or don't you vary it? Whereas if you've got a problem where something equals 0, it's much more straightforward what you're doing. Okay? So one of the reasons, so that was motivation. So what we want to do is we want to take this problem, which uses ordinary geometry, but it's non-integrable. And the idea is, could we go to some new geometry, some extended geometry, where everything is integrable? And if it is, then we can solve things like the moduli problem. Okay. So, I don't know, I've only got 15 minutes. So how do we do this in general? So in general, the idea is we use generalized geometry. And the point is that we extend the geometry so that supersymmetry still corresponds to integrable structures. And along the way, this geometrizes the flux. Okay. So let me just, in the last 15 minutes, let me just give you a crash course on how that works. Is that a good way to go? I can also tell you about other things if you've got other questions. But I guess this is where I'm going. So what's the idea? So let's do the simplest thing. So let's just consider the Never-Schwarz sector of type 2. So what do we have there? We have metric, B-field, and dilaton. Right? And we have the symmetries are diffeomorphisms. And then we have gauge symmetries. So they're generated by diffeomorphisms, right? The change in the metric would be generated by a Lie derivative. And then the change in the B field is generated by a Lie derivative, etc. So they're generated by vectors, right? You're just taking your vector and you're shifting it, taking your coordinates and shifting them by a vector. And then there's also gauge symmetries, and under gauge symmetries, the B field transforms by the exterior derivative of one form, right? Everyone happy? So the whole idea of generalized geometry is that you package these together. So we define a generalized tangent space, E, which is just combination of one forms, vectors and one forms. So if I have an element here, I can think of it as a vector and a one form. So it's got 2D components. Sorry. So I'm putting all my symmetries together into a single object. And then when you do that, some remarkable things happen. So what you find is that the algebra of symmetries corresponds to a sort of generalized Lie bracket. So if you do pairs of ordinarily, if you do a pair of diffeomorphisms one after the other, you get a new diffeomorphism, which is just the Lie bracket of the previous two. So what happens here now is that you get a new diffeomorphism, which is indeed the Lie bracket between the other two. And then you get a new gauge transformation, which looks like the Lie derivative with respect to the old gauge transformation. And then it turns out that you write it in an asymmetric way. So it's not looking very symmetric or anti-symmetric between the primed and the unprimed. I actually had a freedom here because in the variation, it's only the exterior derivative of lambda that appears. So when I define the algebra, I could always shift this by anything, which is d of something, right? Because that won't enter. So I use that freedom to choose exactly this combination. Why do I use that combination? Because it does something very special. So we can think of this whole thing as being the Lie derivative along psi prime and lambda prime of psi and lambda. Right? So I'm going to introduce something which I call the generalized Lie derivative. So if you remember, the Lie bracket is usually, this is just the Lie derivative, one of the other. So I just define this whole thing as the Lie derivative with respect to a generalized vector of another generalized vector. Okay? That's just my definition. When I do that, what happens is that it turns out that there's a natural metric. Let me call it eta of psi plus lambda, psi plus lambda. And I just define it to be the contraction between the one form and the vector. Right? I've got a one form and a vector, I can always just contract them. So if you like, I can also think of this as psi lambda 0, a half times the identity, a half times the identity 0, psi lambda. Why did I choose this? Well, I chose it because it has the special property that when I take the Lie derivative of this metric, I get 0. So you can set up the problem so that there's some preserved metric. And you don't have to put any extra information to define this metric on this generalized tangent space. It's just there, just because you got vectors in one forms. If you think about this metric, it's like a metric in light cone coordinates, right? If you wrote 2 by 2 metric in light cone coordinates, it's 0, 1, 1, 0. So this is like light cone for d coordinates. So this is actually invariant under ODD, which might be familiar as the T-duality group. But we're not doing any T-duality here, we're just doing supergravity. Okay, so by doing this extension, you end up with some kind of geometry, which now, instead of having ordinary vectors, has these bigger 2D component vectors. It's got a natural generalization of the Lie derivative, and instead of having GLD as its structure group, or GL2D as its structure group, it's got this group ODD. Okay. So now let me just draw some analogies. So we had conventional geometry, and there we had the structure group, which was GLDR. We had the tangent space which was Tm. We have the Lie derivative, which is the Lie derivative. And we had a metric, G, which was a OD structure. We had Levi-Civita, and then we could construct the Ricci tensor. Okay? This OD, this is the maximal, well, okay. Let me do generalized geometry. So now the structure group, instead of, so now my tangent space is E, which is Tm plus T star m. The structure group is ODD. Okay, I want to do the dilaton. To do the dilaton, I just have to multiply this by some R plus factor. Don't worry about it, it's just some details. Okay. Note, you can think of this group as SLD, roughly, times R plus. There's a generalized Lie derivative. So here I have an element V, which I think of as psi plus lambda. And then I can define the analog of the metric. That's a generalized metric. And it just turns out it describes exactly GB and phi. And it's invariant under OD times OD. So how do I go from here to here? This is the maximal compact subgroup. Just as this is the maximal compact subgroup of this thing. It turns out you can define the analog of the Levi-Civita connection and torsion. And you can construct the analog of a Ricci tensor, which is some generalized Ricci tensor, which sort of is a section of two copies of it. So, having set this up, I can just do the analog of Riemannian geometry, right? This is Riemannian geometry. I can do the complete analog on this space. When I do that, you find that if you write down an action, which is essentially the integral of the generalized Ricci scalar, what do you find? You find none other than the action of the supergravity. So this is the Nevers-Schwarz supergravity. So the Nevers-Schwarz sector of supergravity is actually just a Riemannian. It's just a pure metric theory, but it's a pure generalized metric. Okay. Now, if you know your Lie groups, so this is SL, that's that Dinkin diagram, right? O2D, that's that Dinkin diagram. These are the two simply laced, right? That means they have no long, all the roots are the same length. You could do one more, which is called exceptional generalized geometry. And now you take the other simply laced Lie groups, which is the exceptional ones. And this just means you take the split form of it. This is the split form, that's the, right, if you know about Lie groups, this is the split form of all the different real Lie groups with the same Lie algebra. This is the split form again, so you just take the split form again. And you can go through the same thing. So the structure group is now this. The generalized tangent space, well, you have two possibilities, it turns out. Tm plus wedge 2 T star m plus stuff. This is M theory in D dimensions. Or you can take it to be Tm plus 2 copies of T star m plus wedge 3 T star m. There are other terms here. That's type 2b. And you can go through the same story, and now again you get, so the generalized metric corresponds to the ordinary metric plus all the gauge potential, all the gauge fields. And if you work out the integral of the Ricci scalar, this is just equal to either 11-dimensional supergravity on MD or type 2b supergravity on MD minus 1. So again, you can think of, if you take 11-dimensional supergravity and you restrict it to a d-dimensional manifold, it's again actually none other than an Einstein theory, but for some generalized geometry. So there's actually 3 natural generalized geometries, which just come from the 3 simply laced Lie algebras. They give you ordinary gravity, they have a Schwarz sector, and either M theory or type 2. Which is pretty bizarre, right? Because you didn't put in any supersymmetry here. We think of these theories as coming from supersymmetry, but I didn't use any supersymmetry at all. Okay, but once you've got this set up, you can now see what you want to do. So it turns out, so for supersymmetric backgrounds, so the eta transforms under the maximally compact subgroup H inside G, really the double cover of that. But so in the ordinary case, it would be SO and spin. In here, the maximally compact subgroup is OD times OD, so it would be spin D times spin D. Here, it depends on which dimension you're in. And then, so this tells you that if you take the pair of the generalized, so too many things are called G. Let's call this something else. Let's call this H. So if I take the pair, the generalized metric, which is all the bosonic fields in the theory, right? Not just the ordinary metric, but everything. And the spinor, this defines a generalized G structure. Right? There'll be a subgroup G of, for example, E dd times R plus that leaves this pair invariant. And then it turns out that SUSY backgrounds correspond to torsion-free generalized G structures. So by extending to the larger geometry, you go from something that was non-integrable with some intrinsic torsion, and also we couldn't quite define the global G structure. These things become nice and globally defined, and now we get something that's integrable. So for example, the fact that it's integrable means that you can calculate moduli. So if you want to know how to calculate the marginal deformations of some background, someone gives you the beta deformed background of like Luna Maldacena, and it says, what are the marginal deformations? That's a hard problem if you set it up normally, but if you set it up this way, you can see exactly where they come from. You can also do the marginal deformations of flux backgrounds, which is an important question if you're thinking about the landscape. Okay, so I haven't shown you any details on that, but I think given the fact that I told you about the ordinary G structures, maybe you can see that there's an analogy at least. And I also haven't justified to you that it's useful, but believe me, it's useful. Are there any questions on that? Yeah.
What if I wanted to look at the Ramon sector?
The Ramon sector? So when I go to the exceptional case, by enlarging the group, I get the whole Ramond sector as well. So here now the generalized metric will encode the metric, B, phi, and all the Ramond fields in the 2B case. In the M theory case, it will enclose the fields of M theory. If I just do dimensional reduction, it gives me the type 2A. So yeah, so you get everything. But it's limited here to saying D is less than or equal to 7. You can probably do E8. It's slightly more complicated. And some people, right, there's people thinking about E9 and so on, right? But that becomes some affine. The algebra's got an infinite number of fields. There's ways of understanding why that's happening. But in generalized geometry, I would just want to limit to D less than or equal to 7. Any other questions? All right, we'll stop, and thanks, and enjoy the pizza.